Parameter servers. Preface. Content of this lecture. In this lecture we will discuss the parameter servers and also discuss the stale synchronous parallel model. In machine learning systems, especially the scalable machine learning algorithms that we are seeing for big data computing requires the abstractions for the scalable building scalable systems. And here we can see that there are three different the machine learning systems landscape. We have to see that there are data flow systems which are built over Hadoop and stack platforms using the graph system algorithms and shared memory systems. And these machine learning algorithms which are nothing but supported as the data flow systems such as naive Bayes and requires an abstraction from the underlying systems like Hadoop and Spark, and for graph systems it requires abstractions from the GraphLab and TensorFlow, and similarly for shared memory systems, and these are Boson and DMTK also requires the parameter servers. So what we will see here is that in a simple case the parameters of machine learning are stored in a distributed hash table that is accessible through the network, which is there in the shared memory systems. So parameter servers which are used in Google, Yahoo, and also is used as an academic work by Smula and Zing. And now we have to see the parameter server and its how it is going to be used as the framework for machine learning. So to build the scalable machine learning systems. So machine learning framework requires the use of parameter server, and it distributes a model over multiple machines and offers two different operations. One is called pull, that is the query part of the model, and the push means update part of the model. So in any machine learning update equation, which is shown here, Wi which is updated as Wi plus little delta is to be handled into the model by push, that is in the form of plus operation. So in a stochastic gradient descent and all in a collapsed Gibbs sampling for a topic modeling, this aggregate, that is the push updates, is done via the addition operation. So whenever this addition operation is there, so these parameters are to be pushed into the model, and that is handled using the parameter server. Now this Spark machine learning is done with the parameter servers. So here in this particular scenario we see that Spark driver and Spark workers, they together work and support this parameter server notion. Similarly, this kind of parameter server notion is also supported in the Glint, and in the Glint we can see there is a Spark, there is a parameter servers, and in a Spark there is a Spark driver and different Spark workers are there. So we can see here in this particular example that that these parameter servers are either maintained in the Glint as the queues, as the distributed queue, and in the Spark as a driver worker combination. So parameter server is used in the training phase also. So in the training state is stored in the parameter shards, and asynchronous updates are being handled. So this is the example figure which shows that the models are stored as a part of parameter shards, parameter server shards, and whenever there is an update, so it has to be updated at all the shards which is managing the parameter server. So the parameter servers are maintained in this big data scenario, that is through the clusters that we are going to understand here in this part of the discussion. So parameter servers are flexible, and here the number of model parameters which is being supported is quite large, and number of cores which are there which supports this parameter server is shown for different machine learning landscape. For example, topic modeling and matrix factorization and CNN, that is convolutional neural networks, and DNN, deep neural networks, all requires flexible parameter servers, and a huge amount of parameters are complex parameter servers are being managed efficiently. Therefore, it is shown here in this example figures. So let us understand about the parameter servers. So parameter server now comprises in Spark comprises of the server machines and the worker machines, and it models the parameter servers as are stored in the parameter server machines and accessed via the key value interface, that is in the distributed as per the distributed shared memory. So extensions of it are multiple keys are available for matrix operations, and multiple channels for multiple sparse vectors, and multiple clients for the same servers. So the extensions which are available here in the parameter server is in the form of push-pull interface to send or receive most recent copy of the subset of the parameters, and the blocking is optional, and the extension can block until the push pulls with a clock which is bounded by t minus rho is completed. So let us see the data parallel learning with the parameter server, and here the parameter servers are shown in this particular picture, that they are being exchanged through different part of the model is available on different servers, and the workers they retrieve the part of the model as it is needed. So therefore, the abstractions are provided which are internally implemented as the data parallel operations in the parameter server, such as the key value APIs for the workers, that is they can get the key and also that means they may get the model values and by get key operation. Similarly, add key with a delta to be updated in the parameter server, and this particular addition can be performed here using add operation. So let us see how the iterations in a MapReduce is supported using the parameter server. So this particular iterations in the MapReduce is often required to implement the scalable machine learning, and this requires the training data to be provided to the different map phase, and which are to be read into different splits or in the form of the shards, and then they will redundantly save the output between these stages in the MapReduce function, and therefore increase the cost of these iterations of the MapReduce, and therefore the parameter servers are very much needed to make this machine learning scalable machine learning support. So this particular parameter servers requires a stale synchronous parallel model. We will understand about them. So here we have to see these model parameters are stored on the parameter server machines and accessed via the key value interface using distributed memory. So iterative machine learning, if we see the workflow which comprises of these parameter transformations, that is the data is transformed and by the worker nodes, and in between they are accessing the model parameters, and for example, in the topic modeling and matrix factorization, support vector machine, and deep neural networks, they all are iterative machine learning algorithms wherein the workers requires these parameters to be updated. Parameters means model parameters are to be updated. So therefore, a parameter server has to maintain this model parameters, and all the workers will now communicate with the model parameters server, and these values are either read, or that means they will either get or they will put these values on this particular parameter server. So here we can see that in typical MapReduce model, where the data model is the independent records and the programming abstraction is in the form of MapReduce, and the execution semantics which is used as bulk synchronous parallel in the MapReduce to support to support the iterative machine learning algorithms. Now, if we compare this with the parameter server, here the data model in the parameter server is also independent records, and the programming abstraction is not the MapReduce, but it is simply the key value store that is in the form of a distributed shared memory to be provided. Now, what is the execution semantics? Is it the bulk synchronous parallel or some other synchronous that we are going to see? Now, the problem here is that the networks are slow. That means when these parameter servers which are maintaining the parameters of the model and using get and add the keys are the operations which are to be performed on the network, they becomes quite slow. As the network is slow compared to the local memory access, so we want to explore the options for handling this with the help of the caching. So now the caching will introduce a problem that is to be handled using the cache synchronization, and here we can see that the cache which is maintained and whenever sparse changes to the model is happening, and if it is done through the cache, then these parameter servers requires this particular cache to be synchronized. That is called cache synchronization. So having implemented the cache synchronization in the parameter servers, the problem of accessing the parameter server across network also can be become efficient if the access is done through the cache. The second solution to implement the efficient access of the parameter server on the network is about the asynchronous operations. So here the machine 1, machine 2, machine 3, they will perform the computation, they will iterate, and now they have to wait till all other iteration they complete their iterations, and then they will interchange their communication, and then the computation can go on. So in every iteration we see that there will be a barrier after the machine finishes the iteration and start the communication, and before all the communication completes, so that the next iteration will begin, and these are the barriers, and if we collapse these barriers, now we can introduce a much efficient way of implementing this asynchrony here in this case. So enable the more frequent coordination on the parameter servers. So if we support this asynchronous execution environment with the parameter servers, then the scenario will look like this, that the efficiency the operations in the parameter server will become more efficient. For example, here the machine 1, machine 2, machine 3, they access different parameters W1 and W2 and W3 from different parameter servers, which are shown logically W1, W2, W3. They are different parameter servers, and they keep on accessing by different machines. and they internally they communicate the results back to this particular server. So this asynchronous operations are, if it is there, then let us see the problems in this asynchronous execution. So asynchronous execution lacks the theoretical guarantees, as the distributed environment can have arbitrary delays from the network and stragglers. So therefore, what we see here is that if we see a particular implementation of the scalable machine learning algorithm, let us say that we say the delayed stochastic gradient descent algorithm. Here we will see that f is a function loss and x is a parameter which is being computed in this algorithm and which required to be updated. And this particular updation, let us see what problem will create during the using asynchronous communication, and therefore we require to make about execution semantics decided, so that this particular asynchronous operation should not be unbounded. So it has to be a bounded synchronous operation which has to be supported. So the parameter servers will use the model which is called stale synchronous parallel model, wherein the global time is let us say t, and the parameter workers will get and can be out of the date, but can't be older than t minus tau. So tau is the tolerance which is introduced, and therefore it is called bounded asynchronous. So tau controls the staleness, also called as stale synchronous parallel. So stale synchronous parallel execution semantics we are going to see here, which is being supported in the parameter servers. So in the stale synchronous parallel, we see here is that they will these are workers 1, 2, 3 and 4. So these workers now they will be changing the parameters asynchronously, and the staleness is also bounded by s is equal to 3. That means the here we can see here is that the worker 2 will be blocked until worker 1 reaches the clock of 2, and so that means the updates will be guaranteed, and this is black means updates are guaranteed, and green means it is visible to the worker 2, and blue will indicate that it is incomplete, and incomplete updates sent to the worker 2, and not yet visible updates not yet sent to the worker 2. So therefore this particular slots which is divided, and staleness bounds s is equal to 3, which is being calculated. So this way the interpolate between BSP and the asynchronous modes, and they subsumes both, allow the workers to usually run at their own pace, and the fastest oblique slowest threads not allowed to drift the clock जो है that means more than s clocks apart. So efficiently it implements the cache parameters in this particular manner. So consistency here matters, because staleness has to be bounded by BSP, which is a strong consistency, but we relax the consistency, and staleness is bounded. So therefore suitable delay will gives a bigger speed up here in this particular case. So stale synchronous parallel, if we introduce, then we will see that it is giving the better result and ensuring the problems of the asynchronous operations. So in this lecture we have discussed the parameter servers and the stale synchronous parallel model of operations which is supported in the parameter servers. Thank you.